7:30, so let's dive straight into this evening's entertainment. Good evening, everyone, and welcome to the mid-October meeting of the Astronomical Society of Edinburgh. I'm Neil Martin. I'm a member of the ASE Council, and I'm standing in for our president this evening, giving him a night off and reciprocating for a good turn that he did for me recently. I'll do a very short intro as to what's coming up next, and then I'll hand over very quickly to our guest speaker this evening, Professor Stephen Smartt, who will be covering the Vera Rubin Observatory and the Legacy Survey of Space and Time. So let's quickly look at what's coming up during October and November. Our October meeting is Square Kilometre Array, Revealing the Hidden Universe with Radio Eyes by Dr. Tyler Burke. And then on the 9th of October, we have our Imaging and Observing group meeting, which is online only. The meetings at the beginning of the month are the hybrid sessions at the AUC, also available on Zoom and YouTube. And then we have a special event coming up on the 15th of October. It's our 100th birthday, so we have a centenary event for ASE members in Edinburgh. Then looking further ahead into November, our meeting in the AUC is the Sloan Digital Sky Survey by Dr. Anne-Marie Wymans. And then on the 6th of November, the following Wednesday, we have our usual Imaging and Observing group meeting, again for members only. So that's what we have coming soon over the next couple of months. So now, as promised, without further ado, I'll hand over to our guest speaker, Professor Stephen Smartt, and ask him to do an introduction and take us into the talk. So if we could just welcome Stephen. Stephen, over to you.
Okay, thank you. Shall I share screen?
Yes, thank you.
There we go. How's that? Can you all see my full screen?
Yeah, absolutely.
Great. Hi. So I'm Stephen Smartt. I'm from the University of Oxford. The Vera Rubin Observatory project. It's an international project, a US construction project, as I'll describe. But the UK, along with France and Chile, are the three biggest international partners. Chile, because the telescope's being built there. France have a long history of helping develop the camera and some of the systems. And the UK will be probably the biggest partner in operations of the facility. I was, up until this month, the start of this month, I was the UK's project scientist for the Rubin Observatory. I've rotated off that position. I have a different position now, and Graham Smith at University of Birmingham has taken over as the project scientist. There's a big involvement from Edinburgh, University of Edinburgh. In fact, they're the lead institution in the UK that leads a large collaboration of UK universities that have joined together and got government money to join the project with work done in the UK, what we call an in-kind contribution to the observatory, and then it will allow us to exploit that. So what I'll talk about is, I'll give an overview of what we've been doing in the area of sky surveys and repeated sky surveys, looking for everything that moves and changes in the sky with small facilities, and then the jump to Rubin, which is an unprecedented observatory and telescope. So the sky has been observed. Rubin's an optical telescope, a very large optical telescope, as I'll describe, but the sky has been observed at all wavelengths, from gamma rays right through to radio. You'll hear about that in the SKA talk coming up. And gamma rays and X-rays, the satellites that observe, they take deep images, stacked images of the sky at those wavelengths, but they also look for things that change at high energy radiation, emit short bursts of high energy radiation, things we call transients or bursts, high energy bursts, gamma ray bursts, X-ray transients. And those satellites, there are many satellites which are observing in the gamma ray and X-ray sky and finding things that change and burst. As you know, as many of you being optical observers, if in the optical, To find something that changes, you have a telescope, you have a detector system, you take an image, you have an exposure time. The length of that exposure time determines the depth of your optical image with a CCD detector, for example. But if you want to decide if anything has changed, if there has been a burst of optical light on that image that you've taken, you typically have to compare it with a reference image and then look to see if those images are different and find things that either move or change. At high energy, the detectors can detect pretty much individual photons and have excellent timing. So they have got usually poor localization on the sky, so poor spatial imaging quality, poor spatial resolution, but excellent timing resolution. Whereas in the optical, of course, you get excellent resolution, depending on the quality of your telescope and the site, but you get excellent excellent spatial resolution, but poor temporal resolution because you don't know when the photon arrived. You've got an exposure time of 30 seconds, 30 minutes. Photons arrive during that period, so you can't tell exactly when the photon arrived during your exposure time. Whereas at high energies, you can tell exactly when that happened. And so combining this, the temporal information and at high energy, the spatial resolution we have in the optical allows us to find things that change right across the electromagnetic spectrum. And the sky, we've got images, deep images of the sky at all wavelengths. The new thing now that's happening both with small telescopes and with the Rubin Observatory is repeated images of the sky, particularly in the optical and the infrared. And if you repeatedly survey the sky, you'll find variable stars, of course, which many well-equipped amateur astronomers have contributed to over decades. You'll find moving objects and asteroids and comets in the data if you're comparing images you've taken with previously taken images, reference frames. And you'll find explosions in the distant universe, supernovae, and a type of explosion that I'll talk about, which we call a kilonova, which is relatively new. Here's a movie that was put together by a colleague of mine at University of California, Berkeley. Image of the galactic plane, and every flash is all extragalactic, well, all supernova explosions since 1054. So you'll see a few dots in the Milky Way galaxy, which are supernovae within our own galaxy, roughly about one a century or so, and then the explosion from the 20th century with extragalactic surveys. So there's the galactic supernovae going off, and then these are the positions of all of the explosions we think are way beyond our galaxy, associated with galaxies throughout the universe. You'll see some structure here. You'll see a stripe come in, or well, I'll just replay that again. You'll see a stripe come in below the galactic plane, which is a survey region from the Sloan. There you see it. That's a survey region from the Sloan Digital Sky Survey, where they picked up lots of supernovae in that region of sky. So we find these supernovae. They're not that difficult to find, depending on your equipment. There used to be up until recently, probably 5 to 10 years ago, there was a huge contribution from amateur astronomers in finding nearby supernovae. But our robotic surveys now, the professional era robotic surveys, are mostly getting even all of the nearby ones. It's only a handful of people. One still very productive astronomer, Koichi Itagaki in Japan, still does discover a reasonable number of nearby supernovae before the professional surveys get there, but he observes a relatively small amount of galaxies quite intensely. Some recent supernovae have been discovered by amateurs, but even now we're mostly getting there with the robotic optical telescopes. So supernovae explosions in distant galaxies. You observe, say, 100 galaxies over 1 year, you'll probably get a supernova in that sample. Our galaxy has produced supernovae at the rate of about once every 100 years, once every 50 years. And I'll explain what a supernova is. Typical way we do it. Here's a nice image of M74. And you can see bright star on the right-hand side of the image here. Here's the supernova, which pops up in a comparison of these two images. These are both from large telescopes, the Gemini Observatory on the left and one of the ESO telescopes on the right. When we do our survey observations, we don't typically get images of this quality. Rubin will produce images of this quality constantly per night because it's a large telescope with excellent spatial resolution. I'll show you some examples of our smaller telescopes that are lower resolution, but they get around the sky very quickly. But basically, we do what we do in an automated fashion is compare images that we've taken over a period of time to look for anything that has changed. And supernovae are one of the most common things that we find. So what are supernovae? Before I come on to the techniques from small telescopes, what are supernovae? They're typically split into two types. The type 1A supernovae from what we call thermonuclear explosions. We're almost certain that these come from, and this has been known for more than 50 years, that these come from the explosions of white dwarfs. These are the dead. White dwarf is the leftover remnant of a solar type star, which has a limit to how massive it can be, about 1.4 times the mass of the sun. Greater than that, it doesn't have enough internal pressure, which is electron degeneracy pressure. These are degenerate cores. They're not burning carbon and oxygen, but they're held up by degeneracy pressure of mostly of the electrons. And they've got a fundamental limit of about 1.4 times the mass of the sun. If they happen to increase their mass above that, and they may increase their mass by accreting material from a companion, or two of them merging together to create a white dwarf that is greater than 1.4 times the mass of the sun, they're unstable, so they start to collapse. The internal temperature rises such that the carbon and oxygen burns in an immediate thermonuclear runaway explosion. The carbon and oxygen that these white dwarfs are made of will burn mostly to heavier elements. Magnesium, silicon, sulfur, and calcium are all produced, but critically, they produce about 0.7 of a solar mass of radioactive nickel. They don't immediately produce iron, which is at the peak of the stable. They don't immediately produce stable iron at the peak of the nuclear binding curve, which we expect to get to during rapid nuclear burning. But nickel 56 is produced. And the reason is that it happens so quickly, you have to preserve the number of protons and neutrons. And the fuel is 2 to 1, carbon and oxygen. And so nickel 56 is 2 to 1. So nickel 56 is radioactive. It will decay in half-life of 6 days to give cobalt 56 and produce 2 high-energy particles and a gamma ray. Cobalt 56 will then decay to stable iron, the stable iron that we see in the universe, that we have on Earth, that's visible throughout the universe. All of the stable iron in the universe is created in supernovae explosions, but not immediately. It's nickel 56, which then decays. Stable iron is extremely stable over a Hubble time. And that is created, cobalt 56 decays with a half-life of 77 days. So it's that radioactivity. It's that if it was just the immediate explosion, then this would just be a blip, and the events would disappear very quickly. They'd be hard to find. But we find things that have got typical lifetimes of days to weeks, and that's determined by the radioactivity, the half-life of these elements, and the amount of material that's ejected. So that nickel 56 powers the luminous explosion that we see and can power the supernova for months and years, and it has effectively a radioactive glow which can last years. So that's one type of supernovae. The other type, typical type, is from massive stars. So massive stars which are greater than 8 times the mass of the sun will grow their cores. They'll burn their hydrogen to helium to carbon and oxygen, as the sun does, but the sun will never get hot enough in the core that carbon and oxygen can burn further. Massive stars, the cores of massive stars will get hotter after the burning phase that produces carbon and oxygen, the helium burning phase, and they can burn carbon and oxygen to the heavier elements, not explosively, but quiescently in their cores. But once they reach iron, then iron can't burn out, stable iron 56, and the iron group elements can't burn by producing any more energy. You have to put energy in to create heavier elements than iron. So that iron becomes degenerate, that iron core, and the iron core then can't hold itself. Eventually, it can't hold itself up. It can't support its own weight by producing thermal pressure through nuclear burning. So the core collapses. And that collapse of the iron core, the release of that core, releases effectively a bomb in the center of these stars. Shockwave goes through the star, and we see the shockwave when it hits the surface. So these two mechanisms are different, the thermonuclear explosions from white dwarfs and these core collapse explosions. To give you an idea, so here's just a schematic picture of Betelgeuse, Antares, Rigel, and Aldebaran. So Betelgeuse, red supergiant, probably a mass of around 10 times the mass of the sun. Its original mass, somewhere between 10 and 15, still disputed exactly how massive it is. Here's the size of the sun roughly times 10 on this image. Now, what explodes here is the core the iron core in a massive star. When you think of a supernova, it's not the star that collapses. It's only the iron core, and the iron core is about the size of the Earth. So the Earth is 100 times smaller than the diameter of this dot here, the size of the sun, which I put on. So it's the size of it's an iron core the size of the Earth that collapses to 10 kilometers. So there are 6,000 kilometers radius, collapses down to 10 kilometers, and that's a neutron. That's typically then a neutron star is formed, and it's the release of energy in that effectively a tiny core of the star in comparison to the overall size of the star that releases the energy. And then that energy, that gravitational potential energy that is released, produces a shock wave that rips through the star. And when it hits the surface gets very hot quickly and expands. And so you've got a big object that's hot and expanding, and that produces the supernova that we see. You also get radioactive nickel-56 formed in these supernovae, and that can keep core collapse supernovae glowing again for months and years. Similar process, the radioactive nickel-56 is formed during this as the shockwave moves through the star, and that decays to stable iron. So that's what we see. Now, interestingly, I think from the perspective of what I do now and what I'm looking forward to do with the Rubin Observatory, when a supernova happens and you form a neutron star or a black hole, you might think, well, that's typically the end. These are dense objects that then will cool away during the lifetime of the universe. But we know now that these dense objects merge together, and white dwarfs the merger of white dwarfs may produce some type 1a supernovae. And we now know, as I'll show you, neutron stars can merge together and release a huge amount of energy and potentially a small amount of mass, which also glows through radioactive powering. So when these objects, these very dense objects, the universe's densest objects, it's not the end of their life and end of their explosive life. They can produce other events. Just to give you an idea of how extreme these dense objects, the densest objects in the universe are, these are things which either create supernovae like white dwarfs, or are the end points of supernovae like neutron stars and black holes. A teaspoon of material, so a teaspoon of white dwarf. A white dwarf is pretty much the size of the Earth, but somewhere between 0.5 and 1.5 times the mass of the sun. So the density of white dwarf material on a teaspoon, that's 10 tons on a teaspoon. That would be the density of white dwarf material. Neutron stars are even denser, so that's the whole of a white dwarf effectively squeezed down from the size of the Earth to 10 kilometers. And they are this number, 6 times 10 to 11 kilograms per centimeter cubed, 6 times 10 to 11 kilograms on a teaspoon. And that's roughly speaking the mass of everyone on Earth squeezed onto a teaspoon. It's the density of an atomic nucleus, because most atoms are mostly empty space with the electrons orbiting around a nucleus. But the nucleus is where all the mass is. And so that's effectively, we're mostly empty space. And if you squeezed all of us onto a teaspoon, you would have one nucleus you would have one object at a nuclear density of of 10 to the 11 kilograms per centimeter cubed. And black holes are objects which are more massive than neutron stars enclosed within a certain radius, which are not, they're not clearly not normal forms of matter, or forms of matter that we can understand. The densest material that we understand is that contained within neutron stars. So a black hole is really more massive and more extreme than a neutron star. We can't probe inside it because we don't see anything beyond the event horizon. Now, transients have been found outside our galaxy and are found on a daily basis. Since 2016, this is sort of the last the last 10 years or so, 15 years of modern surveys of looking at the sky, looking for these explosions, looking for extreme events that are driven by the formation of these dense objects, the merger of these dense objects. We've over 100,000 of these discovered since 2016, which are typically reported publicly to this. We have an International Astronomical Union supernova working group. We run the process of people reporting their discoveries. Amateurs will report their discoveries to us. We'll check them, or other people around the world will check them quickly to see if they really are supernovae or they're something else, maybe an asteroid moving in front of the galaxy. But all of these objects get checked very quickly. They're verified by other surveys, and we find hundreds of them per week now with these robotic surveys. So there are a number. These are the most. I'm just going to give you a few examples here of some of the surveys that I work with and are probably the most successful in terms of surveying the whole sky. And probably for the first time in history, and this is why it's now becoming difficult for amateur astronomers really to make interesting discoveries of nearby supernovae, is that we can get around the whole sky every night, multiple times per night, and have computers process the data. Mostly, you need some humans at the end, but we can mostly do it with computers, process all the data, and find everything that moves or changes within 24 hours, and then repeat that on the next night. Some of the most successful surveys: the Zwicky Transient Facility based in California, the Atlas Survey, which stands for the Asteroid Terrestrial Last Alert System. It's funded by NASA. 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. They're only 50-centimeter telescopes, but their field of view is 25 square degrees each. So that combination can get around the whole sky every night, the whole visible sky every night. And I'm part of the team then that processes the data, finds all the supernovae, and then decides what to follow up. So we're pretty much at the stage where we can get around the whole sky, weather dependent, on a 24-hour basis. There are a few other surveys that have just joined this in the last couple of years, one in Chile and another one in La Palma and Australia, which is joined together. It's a UK-run project. But all of these linked together, we're now serving the sky effectively multiple times per night. And so here are some examples of images we would typically take and the data processing steps. So on the left are images. These are 30-second images taken with a 50-centimeter telescope with our very large at CCD, which is 10,000 by 10,000 pixels. The pixel size is 1.8 arc seconds. I'm sure many of you understand your plate scales and resolution of your images. So these are 10,000 by 10,000 pixel images. Then in the middle, we have the reference frame that we've built up over many years. And then on the right is the difference between the two. So we do a mathematical manipulation of the middle image. We match it to the target image that we've taken, and then we just subtract the two. So we match them in terms of their intensity and the image quality, and then we subtract them. And you can see then in the middle, there are objects there that have popped up, positive sources that tell us there's a source in the target image we've just taken that is not there in the reference frame. And you'll also see there's some noisy sources in the images there. And so the challenge for us in an automated way is to find the real objects, reject all the bogus objects, and don't miss anything. That's our challenge to do in real time, mostly with computers, but we still need a human at the end of this. No one has managed to do this with close to 100% accuracy, precision, and reliability without having a human at the end. And so typically we need someone to look at the images each final images each night. We mostly discovered those types of supernovae, core collapse supernovae, thermonuclear supernovae. We do find things in the last number of years. We found quite a number of very peculiar explosive transients that we're struggling to understand in terms of those two standard paradigms, standard models of exploding stars. I found this one in 2018. I immediately realized its significance because it got bright so quickly. Then I realized, well, it must be extremely luminous, which means it has expanded very rapidly. The speed of that expansion is much higher than you typically see in a supernova, so it must be something unusual. This was detected at radio wavelengths, X-ray wavelengths. The name was 18 COW. COW is just the 2018 COW was the alphanumeric name that we give this as we register them on this transient name server. We keep a record of everything. So it became known as the cow. And this one turned out to be extremely unusual, radiating. The X-rays were very luminous. Radio was very luminous. That means that there's something else going on, not just a thermal explosion. And those most likely come from material that is being accreted onto likely a black hole that was formed, which produced a jet. That's the most likely explanation for the production of the X-ray and radio waves. These are quite rare events. We're struggling to understand why these are produced compared to normal supernovae, or what type of star produces these as they die. Just to give you an idea, so that's the scientific goal, is to find unusual transients and extreme transients. To give you an idea of the challenge, and this is going to be a challenge for the Rubin Observatory. Here's an image from one of the Atlas telescopes. So this is 10K by 10K pixels, 10,000 by 10,000 pixels, roughly 5.4 degrees on a side. Lots of stars and galaxies in that image. Dense image. That's what the difference image looks like on a detector scale. So you subtract off the reference frame. You can see there's lots of bogus sources there, lots of streaks, lots of sources associated with bright stars, which have saturated. And our challenge is then to find the real transients from all of these bogus sources. So typically we will get 20 million detections per day per telescope. And we whittle that down through lots of computer applications of computer algorithms and search algorithms, some artificial intelligence and machine learning. And we get that down to maybe about 200 objects. And then we have people just scan through those 200 objects on a daily basis. And somewhere between 20 and 50 of those will turn out to be real supernovae, extragalactic explosions. So we mostly get computers to do the work, but not all of it. And we typically do that within a couple of days. Now, the interesting thing about this, now, most of them, as I say, are supernovae. Some of them are these unusual things like the cow, which radiate at X-ray and radio if we follow them up. But one interesting thing that's happened since 2015 is this discovery of gravitational waves. And now what we're doing is trying to match our discoveries in the optical, because there we can pinpoint the source, we can see the galaxy, we get a redshift, we can quantify the source of the explosion. But if we can detect it at either other wavelengths or with different messengers, then that adds more to the physics of understanding the objects. And since 2015, gravitational waves, they were discovered in 2015, Nobel Prize was awarded. And in 2000, and there have been several runs of these gravitational wave detectors, and really what they do is sense motions in space, the stretching of space, and that comes from the acceleration of very massive objects. The first one discovered was from binary black holes, and these seem to be the most common sources that produce bursts of gravitational waves. But our challenge is trying to match all of our optical discoveries to gravitational wave detectors, or other things like neutrinos and cosmic ray detections, although that's more difficult. But we've been trying to match our optical observations to these gravitational wave detections to find out what is the source of the gravitational wave, the source of the gravitational waves that we detect on Earth. And as I say, they measure this stretch in space just by measuring the distances along these two arms by a laser. So they're really just big measuring machines. And they can say that a gravitational wave which has stretched space has passed through the Earth and passed through the detector, but they don't know exactly where in the sky it is. They've got a rough idea on the sky, but they can't pinpoint it to, say, a galaxy or a particular star, a particular system. What we do is look for something weird that has happened in that area of sky in the optical at the same time as a gravitational wave has happened. And so since 2017, we've only done this once. And this is where one of the, I think, the great breakthroughs that Rubin will allow is to do this much more regularly and to match these gravitational wave detections with optical light. Let me show you the one that happened in 2017. So I've said most of the things we find, these 100,000 objects we found since 2016, all of the nearby supernovae we've found are either type 1a supernovae from white dwarfs or core collapse supernovae. They mostly fall into that category. There are a couple of other things, but mostly they're supernovae. But in 2017, there was this a detection of gravitational waves from the three detectors, two in the US and one in Italy. But at the same time, there was also a burst of gamma rays, roughly in the same region of sky. And this gravitational wave was called 170817 because it happened on the 17th of August in 2017. And so this shows you, this image shows you time along the x-axis, and the three images above are the gamma ray signal from two satellites, the Fermi satellite and the integral satellite. And you can see here there's a blip and a detection of a weak gamma, quite a weak gamma ray burst, quite a faint gamma ray burst. What you're seeing here in the bottom is the signature from the gravitational wave detector. And you can see that what's happening there, you're looking at frequency versus time. So two objects that are accelerating and causing the gravitational wave are getting closer and closer together. The period's decreasing, the frequency of their orbit is increasing, and eventually they merge. So, and the gamma ray burst was discovered within 2 seconds, 1.7 seconds after the merger of these two sources. So remarkably then, when we went to look in the optical, in this region of sky, when you look at the region of sky from the gamma rays, that's it in blue. If you look at the region which comes from the combined two satellites from gamma rays, that's also it in blue. It's an annulus on the sky. When you look at where the gravitational waves suggested it came from, this is mostly from timing. You get these two bananas shaped here, and combining all of that information ends up with this ellipse on the sky. Everything here is a galaxy within that ellipse, and in one of these galaxies, we find a little faint blip source of light. So you had gravitational waves, gamma rays in an area of sky about 40 square degrees, and in this galaxy, within 12 hours, we found this little source that was not there before. So this faint source in this galaxy, almost certainly, and when we observed it, it's the most unusual thing I had ever seen when we started observing it with our optical telescopes. And this one we call a kilonova, not a supernova, but a kilonova. So what we think has happened here is that this is not the death of massive stars, but it's what has come after the death of two massive stars. So what has happened? There's been two neutron stars. As I showed you how dense they are, how massive they are, they're accelerating around each other in a binary system. That produces the gravitational waves. When they merge, you get a little bit of mass ejected, probably about 5% of the mass of the sun, maybe less, 2 to 5%, radioactive, and it glows for a few days, only a few days. So it's faint, it fades really quickly. And so typically they're difficult to find. Supernovae are relatively easy to find because they last 10 days, month, a week, a year, depending on their distance to us. We can observe them for that sort of period. And you can see from the half-life of the radioactive elements, 6 days, 77 days, they're going to last for 4 months. Here, though, this glow is being produced from very heavy elements in the periodic table, and it fades away extremely quickly. So this is what we saw in that. And this has got this great potential here as I come on to Rubin about really changing this field. You'll notice this is 2017, and we haven't had any discovery like this since. And the reason I think is that these systems are quite rare, but they're also really difficult to find because they're so faint and they fade really quickly. Because what we think happened is two neutron stars merged, probably produced a 2.8 solar mass black hole. Only a little bit of mass was ejected. We got a luminous explosion, probably created heavy elements, and then a short gamma ray burst as well. But these events are extremely rare, but they're very important because they may well produce all of the heavy elements heavier than iron in the periodic table. That's the current best, our current thinking for the best guess, I think, for the source of those heavy elements. So on to the Rubin Observatory. Given that, what do we do now? We're surveying the sky every night with these relatively small telescopes, 0.5 meter to 1.8 meter. Zwicky transient facilities is about a meter diameter mirror. This is a big jump. And the reason it's difficult to build telescopes which have got a large aperture and also a large field of view. Because if you want to survey the sky every night, you need a field of view, a camera that's going to see at least about 10 square degrees, and that's what Rubin has. That's easier to build on a small telescope, given the ratio of the aperture to the focal length, the F ratio of the telescopes. With a large telescope, you typically need a very short focal length to have a large field of view. The bigger the telescope, then the faster the beam is, and that's difficult to correct. So it's been traditionally difficult to build very large aperture facilities with a large field of view. And this is really the first one that's dedicated. So it's being built, and here's a recent image. It's being built in Chile, the northern desert in Chile, the Atacama Desert. It's near some of the other astronomical sites, La Serena. It's close to La Serena. It's near the Gemini Observatory. There are many observatories in the northern desert in Chile. The Rubin Observatory originally was called the Large Synoptic Survey Telescope, and that concept originated in the late 1990s. LSST, the name LSST has remained, but we've changed it to the Legacy Survey of Space and Time. So the observatory is now not called the Large Synoptic Survey Telescope. It's the Vera Rubin Observatory. But the name LSST is commonplace amongst in astronomy and professional astronomy. But we've now just changed it to the Legacy Survey of Space and Time. So the Rubin Observatory will carry out LSST, the Legacy Survey of Space and Time. Here's another image from above. Our projected survey operations will start first quarter of 2025. Here's the telescope. The telescope was built in Spain. This is it on the left. That's it in Spain before it was shipped. And on the right, that's the telescope in the dome. So it's nominally called an 8-meter wide field survey telescope. So if you look at it, it's very compact. It has to be compact to produce the wide field that is required, for which the camera will cover the full field of view that the telescope can provide and have good corrective optics over. So it's a very compact design. Here is I'll show you the optical light path in a second. The key thing is the design of the telescope. Producing a corrected, very wide field, and the camera. The camera is the biggest one that's ever been built for astronomy, 3.2 gigapixels. The bottom picture is a picture in Stanford before it was shipped to Chile, looking down the barrel of the camera, and you can see all of the individual CCDs there. They're 4K by 4K individual CCDs. So the focal plane is made up of a mosaic of detectors. The image in the top left is an image of the lens, one of the lenses, which will sit in front of the camera, and I'll show you the light path to show you the construction of the telescope. Here's an image that was taken in the lab in Stanford, and it's an image of Vera Rubin. So Vera Rubin, she was one of the, along with Zwicky, the discoverer of dark matter. So she looked at the rotation curves of nearby galaxies and inferred there must be more matter in the galaxies than we can see from the stellar light. You can see the image of the moon there. So that's the size of a full moon compared to the field of view of the camera itself. So it's called the Charles Simonyi telescope. He was one of the first donors to the project. So full diameter is 8.4 meters, but in reality, the actual effective aperture is 6.5, and I'll show you why. So this is the optical system. And that's where, so it's got a primary mirror down here. It's got this inset, which I'll come to in a minute. The secondary is up here, and then a 3-lens system before it hits the focal plane. So the light will come down and hit the primary, reflect up, hit the secondary. Secondary, I think, is 3.4 meters. It goes down, the light comes down, hits the tertiary. So the tertiary is inset into the primary mirror, which means it's not primary collecting area of the telescope. That's why it's the whole primary mirror assembly is 8.4 meters in diameter, but the effective aperture of the primary is really 6.5. And then it reflects up off the tertiary mirror through the lens system into the camera. So the camera sits above the primary mirror. That's the optical layout. So we're at the UK. We're involved in the data processing for Rubin. So what I showed you for the small telescopes, where we process the data, we do the image subtraction, we classify all of the sources. So we were part of we have built a system to do that jointly between Queen's, University of Belfast, Oxford, and Edinburgh. We're the 3 main institutes that are building this system. So what will happen is the data will be processed in the US, and then the sources that are found will come out in a stream of 10 million sources per night. And our job is to classify them and pass them on to scientists. And so the telescope will do that every 30 seconds for 10 years. It will take an image, produce new objects, and then we have to filter them and make sense of them. So there's lots of machine learning and AI goes into this, fitting these sources with models, and then filtering them to find out what we think we need to pay attention to. And that's the challenge, getting through, first of all, the real junk, which are spurious detections, but then also filtering out the variable stars, the solar system objects, and classifying them in real time. And we have to keep up with the data. So it's a big challenge. This is a big computing and infrastructure challenge. We'll have these 10 million sources being put out per day. Probably within those, there'll be 1,000 supernovae. Most of those 10 million alerts will be moving objects in the solar system and variable stars. And we will be looking at 1,000 supernovae per day. And I think, I'll mention this at the end, I think we've a chance, although I said, those kilonovae that are associated with gravitational waves, they're really interesting scientifically. They may produce all of the heavy chemical elements. We've only got one. I think with Rubin, we've a real chance of finding tens of these sources. And the reason they've been difficult to find is because they're so faint. And when we find these things with Rubin, then we'll feed the James Webb, for example, in the future extremely large telescope. So it's a big challenge, computing challenge for us, but the UK are really playing a central role in the operations, not in the construction, but in the operations of the facility. So what will it really produce? I mean, something like James Webb, you've seen the images from James Webb, and they really have the wow factor where we look at the sky in a different way. We haven't looked at the sky at that resolution, at that wavelength, in those infrared wavelengths before, and those are really new images. Now, Rubin will not give us, it's not new. We've looked at the sky at the depth of Rubin and the resolution of Rubin from the ground. We've done that with all our large telescopes. We've got plenty of 8-meter telescopes on the ground. So what is it that it can do that is really new? And here, I think this little movie captures it well. This is taken from the Subaru telescope, the Japanese telescope, which is on Hawaii. And this is a zoom in of a rich galaxy cluster. You can see great detail here on the galaxies, the big galaxies, elliptical galaxies in the core of the cluster, and all of the other fainter galaxies around it. Very high resolution from the ground. But let me just give you a sense of what Rubin will do. So that's an image of the whole sky. Here's a region of the sky that has been observed by quite large telescopes, but it's a small region that's been observed in great detail. And this is highlighting interesting sources, mostly galaxies and galaxy clusters that are there. Then zooming in, this is the region, this is what Subaru, an 8-meter telescope, has observed. And that's the image quality and resolution we'll get from Rubin. But we're going to get that over the whole sky, and we're going to get it repeatedly. So as this zooms out, keep that detailed image in your mind. And as we zoom out, think of we're getting that resolution, that depth, but now over the whole southern sky, not the whole sky, because it's only in the southern hemisphere. But I think that captures what this telescope can do, and it can repeat on a nightly basis. I'll give you another example. On the left, that's our current best digital image of the sky, of the whole sky, from the Sloan Digital Sky Survey, from Pan-STARRS or DECAM. They're all similar sort of depth. And on the right is what we're going to get from LSST, the Legacy Survey of Space and Time. So it'll be revolutionary in its depth, and the repetition night after night will really be a game changer for us. I'll just skip this and I'll say finally what I think. So we'll go deeper than all of the other surveys. We'll go find objects which are further away. We'll do that over the whole southern sky. What I think is really interesting is finding these very faint sources, potentially linked to gravitational waves, which we haven't been able to do before because they've been mostly very faint and they fade really quickly. And if I can highlight that, this is the one source from 2017, quite nearby. This is an image of time versus luminosity or magnitude. So here's a typical supernova light curve. So it rises over a period of about 2 weeks and then fades away over a period of months. So they're relatively easy to find. They're there for a long time. But these kilonovae, which are from merging neutron stars, are much fainter, probably a factor of roughly 40 to 50 fainter, and they decline really quickly. In the optical, they decline within 5 days. So these things are they're rare, they're faint, and we just realized probably in the last year, they can occur quite far away from their host galaxy. So this is the only other real kilonova candidate we have. And look where it is compared to its host galaxy. It's an enormous distance away. So trying to find these, associate them with galaxies when they fade really quickly and they're faint is a real challenge. But I think this is one of the things that I want to do. I'm leading a team that will try and find these and link them with gravitational wave sources with when Rubin starts to observe. And we've got approval from Rubin. We're allowed to interrupt the schedule and observe the regions of gravitational waves to try and find these new things. So I'll just finish off by saying this is a big UK consortium. Virtually every university that has an astronomy department in the UK is involved in our collaboration called LSST UK and the Rubin Observatory. There's great synergy around the UK we've got great history, particularly in Edinburgh, Cambridge as well, in terms of surveying the sky, managing survey data, releasing that to the general astronomical community. There's real heritage there. I think that's why we were an attractive partner to the US. But to conclude, this is the biggest camera ever built on the biggest survey telescope that's ever been built. It's got the highest data rate that we've ever seen. It'll be 100 times more sensitive than our current sky surveys. And so from faint solar system sources, things beyond Pluto, trans-Neptunian objects right out to the highest redshift, it will certainly break new ground. And what I'm really interested in are these faint, rare explosions, potentially in nearby galaxies that we may have missed up until now because they're just too faint and too fast. But matching those detections with nearby galaxies and gravitational wave signals, I think there's real scientific opportunity there for us to find new things. And as I say, these may harbor the gold, scientific gold, because they're so interesting, but these may be the sources of all the gold in the universe and all of the heavy elements. So I'll leave it there. Thank you.
Thank you very much indeed, Stephen. That's absolutely fascinating. If everyone could come off mute and well, let's thank Professor Smartt in the usual way. And let's open it up to questions on Zoom. Does anyone have a question?
I'll ask a question. If you know, I mean, I'm just wondering, assuming this is all successful and you find all these things, what do you think you're going to discover from it?
Yeah, so there are a number of science questions that Rubin wants to answer. From my perspective, or if we can find more of these kilonovae, these unusual faint explosions that are likely to be mergers of neutron stars, are there enough of them that they would produce all of the heavy chemical elements that we see on Earth? So everything heavier than iron. So we obviously detect, detect them on Earth. We know how abundant they are in the solar system, but exactly where they're produced, we don't know yet. We think they are produced in these. They're certainly produced to some extent in these neutron stars. Whether or not all of the elements are beyond iron or produced in neutron star mergers, or the majority of them, is still an open question. And I think the two of the other things which are potentially really interesting are the population of asteroids beyond Pluto, trans-Neptunian objects. So this will be, because it will survey the sky continually, it will find the smaller, it will probe smaller objects beyond Pluto than we've had the potential to do before, or things which are further away, which might be Pluto-size objects, but they're further out even beyond Sedna, for example. So I think there's a real opportunity to do a census of the solar system to depths that's never been done before. And another thing is the high redshift universe, finding supernovae in the high redshift universe that can give us an idea whether dark energy really is a constant or if it's changing. Those are three sort of science examples that people, I think, are really excited about.
Thank you.
Fran and Nigel, you have a question.
Yes, thanks very much, Stephen. That was absolutely fascinating. Because you're calling the survey now the legacy survey, I'm assuming that you see this program extending into the future. Do you have any kind of time scale for how long this program is going to run?
So yeah, the operations are funded for 10 years. Once it starts survey operations next year, we hope, then there's funding in the US and through the international partners for the last 10 years. Beyond that, then there'll have to be a decision about what is done with the facility, but the core program will last that period of time, almost certainly.
And do you see various groups combing through this data for a long time to come?
Yeah, definitely. I mean, so the things that change and that come out as alerts, so the supernova explosions and variable stars and active galactic nuclei, people will be looking at those from sort of day one, when they're being produced. But then every year there'll be a data release, which is everything co-added together to get deeper and deeper. And by the time you get to 10 years, then it'll have the full 10-year depth. And people will be, I think, this will be the definitive optical image of the sky for probably 50 years, I would say.
Wow. Okay. Thank you very much.
Jonathan, you're next for questions.
Yes, my question was the sources that you mentioned were far away from their host galaxies. Why do you think they would be so far away?
Yeah, good question. So this one is this one that we found, which we think is almost certainly associated with this galaxy. Just let me show you this. So why these? Why is that so far away? So we do see supernovae that are at these large distances. They're rare, but it does happen. If this is produced in a binary system, so if we think this is two neutron stars in a binary system, when one of those, potentially both, but certainly when one of those has formed a supernova, supernovae tend to be slightly asymmetric, and as the core collapses and the shock wave goes out, you can get a slight asymmetry, which causes neutron stars to have quite high velocities. And we see neutron stars with very high velocities in the galaxy, up to like 500 kilometers per second. And the binary system there are certain configurations of the binary system in which it can remain bound, but the whole thing gets a kick of a few hundred kilometers per second. And a few hundred kilometers per second over several billion years will take the source to this distance. So you need to have a kick. Probably it was formed in the galaxy, and one of the two supernovae produced a kick, typically compared to what we see in our own galaxy, similar to what we see for the neutron stars. But the whole system moved out there at that speed, and it roughly works a few hundred kilometers per second at a few billion years.
Okay, thank you. That was fascinating.
Thanks, Jonathan. And next up is Andrew Farrell. Andrew.
Well, thank you very much. That was an excellent talk. Let me ask the inevitable question. Today, I think I was reading where the latest Starlink modules are creating havoc in the radio telescope world.
Yeah.
To what extent is it going to nullify some of the work you're doing or interrupt some of the work you're doing? And how can you counteract that in the analysis?
Yeah, so they are a real problem. And we see them constantly in our smaller aperture facility surveys. They're a bigger problem for Rubin because of the size of the collecting area. You're collecting more photons from them, collecting more charge in the detectors, so it creates more of an issue with the saturation of the streak in the detector that we're going to see. Can create what we call persistence. So the next image might have that charge there. So Rubin are quite worried about this. The mitigations that we're currently using with our smaller facilities are Starlink will tell us where they are, and so we can point during twilight in particular, because usually most of the problem is at twilight. So when they're reflecting light from the sun, so during the middle of the night, when they're around the other side of the Earth, they typically don't get illuminated by the sun. The worst time is during twilight. Unfortunately, that's the best place to look for near-Earth objects, is down low in the sky, typically in the directions where they're bright. We can't avoid them. They have mitigated in some way. They have used different types of paint, and they're experimenting with different types of paint. They're also experimenting with the orientation, and that does make a difference. I think Rubin will be affected much more than the smaller facilities, just because of the aperture. And mostly they're thinking it's really repeat the observations that have been done, and we lose time, observing time is basically money. It takes you longer to reach a certain depth. So I think it's going to cost in terms of the overall financial profile of the observatory. It's currently not a showstopper with the current numbers. It just means being more careful at twilight and repeating observations.
Thank you. One assumes as other countries take the concept of Starlink,
yeah,
it's just going to get worse and worse.
Well, I think that's the real worry, that it's the Wild West where there's no regulation. Starlink, although they're the major contributor at the minute, at least they are talking to professional astronomers. You get another company that just doesn't care. You get, someone from China or Russia or somewhere just doesn't care, puts things up. And I think the worry is also you put things up and they go bust, the company goes bust, and the satellites are left there, they're not doing anything, and they don't care. So I think it's it's that increase in numbers which really worries us. And the higher up they are, then the longer during the night they're observable. So if they're down around, if they're below, what is it, around 600 kilometers, say, we're typically low Earth orbit. It's not so bad. If they go higher, that's more of a problem. But of course, if they go higher, then it's more of a problem for them to communicate from the ground. So they have a trade-off. I think the radio astronomers it's more of a worry for them because of the contamination. I think for optical we can work around it. It costs, but we can work around the current projections. But the worry is, much larger numbers that are unregulated.
Thank you.
Great, thanks, Andrew. I'll indulge myself and ask a question if I can. In terms of the machine learning and AI algorithms and the human intervention, is there a target to remove that human intervention, or will it be the case that there'll always be something that we can do with our Mark 1 eyeballs?
Yeah. Yes, I think the target is to try and minimize our effort because the people we have on duty every day, it's not their most enjoyable activity of searching through the real and the bogus. When they find something, it is, then they get excited about it. But reducing that effort definitely is. We're continually trying to improve that. I think most surveys are getting down to the same type of performance. There are a number that have said, we can trigger right through start to finish without a person in the loop. I think that's true, but not consistently for every object. You can cherry pick the good ones that are the bright ones, the obvious ones, nearby a galaxy, do all of that very, very robustly and pick out some of them that are clearly real without anyone having to look. And we're pretty close to that as well. But I think doing it consistently, we're not an understanding exactly where the algorithm goes right and wrong at the finer details is not there yet. We certainly do want to improve it. We'll be able to improve it. But it's not clear we'll really be able to get to the completely do it all. You still need someone to check it.
Great, thank you. Norman, you have a question.
Yes, I'm just curious, because you're working in visible light, you presumably can't see quite as far back as the James Webb. So sort of really ancient supernovae are out of sight, are they?
Yes. Yeah. So there's a certain there will be a certain redshift where the supernovae, most of the light is shifted from the optical to the infrared, and then they become very faint in the observed optical light that we're looking at. Effectively, we'll be looking at the UV ultraviolet the rest frame ultraviolet emission shifted into the optical. And type 1a supernovae, for example, are very faint in the ultraviolet. So there's a certain redshift beyond, say, redshift 2. We won't get very many type 1a supernovae because we'll be looking at the UV and they're so faint we just won't get them. There's the supernova surveys for cosmology with Rubin are not aiming for those really high redshifts. They're aiming for a redshift about 0.5 to 1, where they can pick them up in the optical. But the advantage of Rubin is just the sheer numbers that it will find and the systematics, not really pushing it to higher redshift. But you're right, we will lose them at that redshift, and we just can't get them because the light's gone in the infrared.
Okay, splendid. Thanks you, Norman. Jim, I think you were monitoring YouTube for us. Were there any questions from our YouTube audience?
I had a quick look and there was no comments on YouTube.
Fantastic, Jim. Thank you very much. Okay, well, I think that brings us to the
There are
end.
two questions on the chat, Neil.
Oh, thank you, Mike. Did I miss those? Oh yeah, oh yeah, good. From Glow. Glow, are you on? Did you want to ask your question? Oh no, I can see the follow-up comment. Are there campaigns for international legislation for the sky debris and travel?
Yes, so there are a number of organizations around the world. And Andy, I don't know if you know Andy Lawrence from University of Edinburgh. I don't know if he's
yes.
Yeah, so Andy's very active in trying to coordinate both UK and international communities to try and get legislation at this level, you know, of international agreement about what can and can't be done. So the International Astronomical Union is active in this as well, and is becoming more so. So yes, there are campaigns. I think it is the way to go, is to try and get some regulation agreed at you know, between first of all probably the space agencies and then government level. But there's certainly lobbying going on by a number of organizations.
Okay, thank you, and thanks for the question, Glow. And Jim's asked a question. Jim, do you want to come off mute and ask your question?
Thanks very much for the talk. Very interesting. I was wondering, that for the kilonova, there's a time delay between the gravitational signature and the peak of the optical signature. Just wondering, use the distance measurement at all?
So it's a very interesting question. The time difference between the gravitational wave arriving and the first photon arriving. Now that typically isn't used. There's a different way to measure distances. It's not that. The time delay is actually some of the theories of dark energy and alternative gravity theories actually came up with suggestions that gravitational waves would move at a different speed to light. They wouldn't move at the speed of light. But the fact that we effectively saw the gamma rays and the gravitational wave arrive at the same time has ruled many of those theories out. So it's been used as a test of fundamental physics, that difference between the timing between the GW signal, which is a very good measurement and very precise measurement, and the gamma ray detection, which is also a precise measurement. In the optical, it's a little bit more uncertain because it depends on, you know, how you define the optical peak when you observe. So when you decide to go and take an observation, which is not exactly, we're not observing at exactly the same time the gravitational wave was detected, but we have to go point the telescope, take an exposure. So the exact timing there is uncertain. But where the distance, the interesting thing about distances is that with the gravitational wave signature, from Einstein's theory of general relativity, it does provide a very good estimate of distance. So the strength of the signal and the frequency of the signal, you can estimate the distance to the source. And if you get a redshift of the host galaxy, that's another way of measuring the Hubble constant. So that's really interesting for cosmologists. You need about 50 of them to make a measurement, a real proper measurement of the Hubble constant. So people are trying to want to do this with the neutron star mergers. You need the kilonova because you need the host galaxy and the redshift. But the distance comes from the gravitational wave signature itself.
Thank you. Very interesting.
Thanks very much indeed, Jim. I think I've spotted a couple of questions that have just popped up from the YouTube channel. Any thoughts? So this is Alan Arnson. Any thoughts on the correlation between cold matter and the effects on the edge of galaxies? The effect of cold on space and how matter and stars behaves at ultra low temperatures?
So I think the temperatures we get in space, they're typically not as cold as you can get in the lab. So the really ultra cold stuff that is done in the lab is often even more extreme than we'll find in the interstellar medium. Like the temperature of the CMB is 2.7 Kelvin, but we can get way below 2.7 in the lab. So the extreme cold that you get, it's the really low density is the extreme if you think of what's the extreme conditions we're measuring, for things like kilonovae and supernovae, it's really high temperatures and high densities. In the lowest density regions in the interstellar medium is typically the very low density, but the temperatures typically aren't that low compared to what can be achieved in the lab. Probably more interesting is this idea of cold dark matter, which is actually not that cold. But it's not hot in terms of astronomical terms. It's not high velocity and warm. But that searching for cold dark matter on the edge of galaxies is extremely interesting, which is something that Rubin will try and do, with trying to map the profile of mass around galaxies particularly from gravitational lensing.
Okay, splendid. James Christopher Hunt from Washington, DC. As a former student of Joseph Weber, I was delighted to hear the upcoming focus on gravitational waves. That's more a comment than a question.
Yeah, very interesting. Yeah.
Oh, there is a question about quark stars. About 20 years ago, these were announced as a possible remnant of supernovae. What's the latest on this?
Yeah, so I'll be honest, I haven't followed that in detail. So there've been a number of suggestions of these, I think what are called quark novae, and I don't fully understand the physics behind those, that have been suggested for some types of peculiar transients. Still viable, I think, that idea, but I haven't kept up with the literature on that. It hasn't been adopted as a mainstream idea for most of the exotic transients that we've discovered. I think the other explanations for them, particularly involving very fast rotating neutron stars, accretion onto black holes, I think have produced models that have matched the data better than the quark novae ideas. But as I say, I haven't followed the literature on that particularly closely.
Okay, splendid, Stephen. Thank you very much for answering all of those questions from the collective audience and those on YouTube. So let's thank Stephen again for his talk again this evening. Fascinating. I think everyone agrees on that.
Yep.
Thank you.
And that brings us nicely to the close of the session this evening. And of course, it is mid-September and not October, as I said in my introduction. Thanks for pointing that out.
Space time.
Spaced out time.
So thanks everyone for a very enjoyable evening, and look forward to seeing you all next time.